Hello everyone. Today we begin our discussion on one of the core tasks in data mining, classification. We'll follow Chapter 8 from the textbook Data Mining, Concepts and Techniques by Hahn, Camber, and Pei. In this session, we'll go over basic classification concepts and explore how decision trees are used to classify data. This chapter focuses on basic concepts of classification, decision tree induction, Bayes methods, rule-based classification, model evaluation, ensemble techniques to improve classification. Let's begin with the fundamentals of classification. Classification falls under supervised learning. This means the data used for training includes known class labels. The model learns patterns from this labeled data to classify new, unseen data. In contrast, unsupervised learning doesn't have labeled data. Clustering is a common example. The goal is to identify patterns or groupings in unlabeled datasets. Classification predicts categorical labels like yes or no. It builds a model using training data that maps input features to class labels. In contrast, numeric prediction predicts continuous values, like predicting the price of a house. Common applications of classification include credit approval, medical diagnosis, fraud detection, and content categorization. Classification involves two steps. 1. Model construction. The algorithm learns from the training data to build a model, such as a decision tree. 2. Model usage. The model is then used to classify unseen data. We evaluate accuracy by comparing predicted labels to actual labels in a separate test set. Important, training and testing datasets must be separate to avoid overfitting. Here's a simple example. We have a training dataset with attributes like rank and years. A classifier may learn a rule like, if rank is professor or year 6, then tenured equals yes. The classifier learns such rules from patterns in the data and uses them to predict future cases. Once the model is trained, we can use it for predictions. For example, given a new instance, Jeff, Professor, 4, the model will predict whether Jeff is tenured or not. The goal is to generalize well, perform accurately on data it has not seen before. This slide reiterates the flow of our chapter. We've just covered the basics. Next, we'll dig into decision tree induction, one of the most popular and intuitive classification methods. Here's an example decision tree based on data about computer purchases. The decision is based on attributes like age, student status, and credit rating. It splits the data based on the attribute that best separates the classes at each level. The decision tree algorithm works in a top-down fashion. It begins with the entire dataset and recursively partitions it based on attribute values. The key decisions are: which attribute to split on, when to stop splitting. It uses statistical measures like information gain to decide splits. Entropy measures the uncertainty in a dataset. Lower entropy means less impurity, so the goal is to reduce entropy with each split. For two-class problems, the entropy formula helps determine how well an attribute separates the data. Information gain is used to decide which attribute to split on. It measures the reduction in entropy after the dataset is split on an attribute. We calculate 1. Overall entropy of the dataset. 2. Entropy after splitting on an attribute. 3. Information gain equals overall entropy, split entropy. Let's take the attribute age. We divide the data into three groups: less than or equal to 30, 31.40, greater than 40. For each group, we calculate the entropy using the number of yes and no class labels. Attributes with higher information gain are preferred for splitting. This table shows the detailed calculations for the age attribute. Less than or equal to 30, 2 yes, 3 no, entropy equals 0.971. 31.40, 4 yes, 0 no, entropy equals 0. 40, 3 yes, 2 no, entropy equals 0.971. The weighted average of these gives the split entropy. When attributes are numeric or continuous, we can't split on each unique value. Instead, we consider midpoints between sorted values. We choose the split point that gives the minimum expected entropy. This approach helps adapt decision trees for continuous data. Let's now explore the Gini index, a popular attribute selection measure used in the CART algorithm and tools like IBM Intelligent Miner. The Gini index measures the impurity of a dataset. For a dataset D with n classes, it is calculated as 1 minus the sum of squared probabilities of each class. When a dataset is split using attribute A into subsets D1 and D2, we compute the weighted Gini index for the split. The attribute that results in the lowest Gini index, or the highest reduction in impurity, is chosen for splitting. Here's an example to understand how the Gini index is computed. Suppose our dataset has 9 positive and 5 negative instances for the class BYS_computer. We consider splitting on the attribute income into subsets like low, medium, and high. For each subset, we compute the Gini value and then take the weighted average. The best split is the one with the lowest combined Gini. In this case, splitting on low, medium versus high gives the lowest Gini index. Let's compare the 3 main attribute selection measures. Information gain is simple and effective but tends to favor attributes with many distinct values. Gain ratio addresses this issue but may prefer splits that isolate small groups. Gini index also works well but can struggle when there are many classes. It prefers splits that produce equal-sized and pure partitions. Each method has its own strengths, and the best choice often depends on the data. Besides the standard methods, other attribute selection measures are also used. CHAID relies on the chi-square test for independence. CSEP can outperform information gain and Gini index in certain scenarios. G-statistic is similar to chi-square in behavior. The MDL principle prefers simpler trees that minimize the number of bits needed to encode the model and its errors. Some models like CART also support multivariate splits based on combinations of attributes. One challenge in building decision trees is overfitting. A fully grown tree might model noise in the training data, reducing its performance on unseen data. There are 2 strategies to address this: pre-pruning, where we stop splitting a node early if it doesn't improve accuracy beyond a threshold, and post-pruning, where we build the complete tree and then remove branches using a separate validation set to identify and cut irrelevant branches. Several enhancements have been introduced to improve basic decision tree algorithms. These include support for continuous valued attributes by dynamically discretizing them, and techniques to handle missing values by assigning either the most probable value or distributing instances probabilistically. Another enhancement is attribute construction, where new attributes are formed by combining existing ones to reduce data fragmentation and increase interpretability. Scalability is a major concern in data mining. Modern classification algorithms must handle millions of records with many attributes efficiently. Decision trees are widely used because of their fast training speed, interpretability, and ability to translate easily into rules or SQL queries. One scalable algorithm is Rainforest, which builds AVC lists, attribute, value, class label mappings, to separate tree quality from scalability concerns. The Rainforest framework introduces the idea of AVC lists. These lists summarize how each attribute's values are distributed across class labels. An AVC set is created for each attribute by projecting the dataset on that attribute and aggregating class label counts. An AVC group at a node includes all AVC sets for the attributes at that node, enabling efficient tree construction even for large datasets. This slide shows the AVC sets for attributes such as income, age, student status, and credit rating. For each attribute, we count how many times each value occurs for each class label. For example, under student, we see that yes appears 6 times with a yes class label and once with a no. These AVC sets allow the algorithm to compute splits efficiently without scanning the full dataset at every node. BOAT, or Bootstrapped Optimistic Algorithm for Tree Construction, is another scalable decision tree method. It uses bootstrapping to generate multiple smaller training samples. Each sample is used to build a partial tree. Then, these trees are analyzed to construct a final tree that approximates what we would get using the entire dataset. BODE is efficient, it only requires 2 full scans of the database and supports incremental learning. Once classification is complete, results can be presented in various formats. Decision rules, tree visualizations, or performance metrics such as confusion matrices and accuracy scores help users interpret the model. Effective presentation is key to understanding and validating the classification outcomes. This slide presents a sample visualization of a decision tree created using SGI's Mindset 3.0. Visualization tools like this help analysts explore and understand decision-making paths in the tree, track attribute importance, and detect patterns. Such tools improve the interpretability and trustworthiness of the model. Finally, we have an example of interactive visual mining through perception-based classification or PBC. PBC emphasizes user interaction and visual feedback, making it easier to detect insights and refine the classification process. Such tools empower domain experts to actively participate in data mining without needing deep technical expertise.